there are other icy bodies in the solar system that are of interest to astrobiologists and might be places even to look for life. One of them is Triton, which is the moon of Neptune. It's a very unusual moon because it orbits backwards around Neptune, and this is thought to mean that it might have been captured by Neptune early in its history rather than being formed with Neptune at the time that the solar system formed. Like other icy bodies, it has a surface layer of ice which is a mixture of nitrogen, methane, carbon dioxide, carbon monoxide and water, overlaying a water ice-rich mantle. It's got a lot of impact craters on its surface, and this suggests that the surface may be very ancient. It probably hasn't been active for hundreds of millions of years. We think that perhaps Triton was subject to gravitational flexing in its early history when it was first captured by Neptune, but now is essentially inactive. So although the surface of Triton may be inactive now, what about its early history when it was first captured by Neptune? Maybe it had an interior ocean. Maybe there's even liquid water buried deep under the surface of Triton today. This moon would be a lot more challenging than, say, Enceladus, that's spewing out water vapor into space to sample, but it might be a place where we could look for evidence of life. For example, we could look on the surface of the moon and see whether any materials from the deep interior of the moon have been welled up onto the surface in its past, and which we could sample and study possibly organic chemistry in the interior of Triton. So even around Neptune, there's interests for astrobiologists. In an earlier lecture, we spoke about Europa, one of the moons of Jupiter. There are other moons around Jupiter that are worth studying as well, such as Ganymede. Ganymede is a little bit like Europa. It seems to have a metallic core surrounded by a rocky inner mantle, and then again a liquid water ocean, a salty ocean with a cold, icy surface over the top of it. Ganymede, like Europa, could also be a site for the study by astrobiologists to see whether that salty ocean beneath its surface is a location for life. We could go really wild and speculate about life in Pluto and Charon, its largest satellite. We don't know much about Pluto and Charon. We have to rely on telescopic data. But NASA's New Horizons probe will fly by these objects in 2014 and give us more information about them. There is some speculation that they too might be icy bodies, and possibly Pluto might even have an ocean beneath its surface. Well, all this is speculation, but it shows how even in the furthest reaches of our solar system, there may be objects of interest to astrobiologists, even for understanding the chemistry of potential life. Over the last few decades, one of the most interesting moons, apart from Europa and Enceladus, has been Titan, one of the moons of Saturn. It's the largest moon of Saturn and the only moon to have a dense atmosphere. It's got an atmosphere of nitrogen and organic compounds, and it's the only place except the Earth with stable bodies of liquid on its surface. Most of the information that we have about Titan comes from the Huygens probe that landed on its surface in 2005 and took measurements as it passed through Titan's atmosphere. We saw that the surface has mountains, river valleys and all sorts of features typical of erosion by wind and rain, just like we see on the Earth. But the big difference is that Titan has rivers and rain of liquid methane instead of water. This is a very, very different world. The methane is processed high up in the atmosphere and produces complex organic compounds that then rain back down onto the surface of this moon and forms these features that we see on the surface. The interior structure of Titan is also very interesting. The surface features of the moon appear to move around, and this suggests that there is a liquid over which the surface is moving. What we think is that the interior of Titan has a silicate rocky core, and above that a high pressure layer of ice, in fact a particular type of ice called ice 6. And then above that maybe a global subsurface ocean, and then over that an outer shell made of water ice, and then a surface made up of organic rich materials, just as was observed by the Huygens lander. Well, why is all of this interesting? Well, first of all, Titan gives rise to interesting speculations about the possibility of life using a solvent other than water, for example, liquid methane. It's probably quite unlikely, but nevertheless Titan could be a very interesting laboratory for understanding how organic chemistry works and how complex chemistry can occur on a surface where there's no liquid water but plenty of liquid methane to generate new types of chemistry. This complex organic chemistry could also give us ideas about prebiotic chemistry, the chemistry that was necessary to give rise to life. How did the building blocks of life form on the early Earth? By looking at Titan and thinking about Titan as a giant chemical reactor, we might be able to learn something about how simple molecules like methane and ethane are processed into more complex molecules that might eventually lead to building blocks like amino acids and sugars necessary for the evolution of life. So Titan is a window, if you like, to the possible organic chemistry that might be necessary for the origin of life. Equally intriguing is the possibility that this organic-rich surface might be in contact with this proposed subsurface ocean underneath the surface of Titan. If it is in contact, could it be that this subsurface ocean on Titan harbours life? Well, again, it's very difficult to speculate reliably on this possibility, but Titan is yet another moon with an ocean possibly beneath its surface that might be a habitat for life. So what have we learnt in this lecture? Well, hopefully we've learned that there are a number of possibilities for life in icy bodies in our solar system. There are many objects for astrobiologists to explore, and even if these moons don't have life, they will reveal new insights into chemistry and the chemistries that might give rise to life on other planetary bodies. We've learned that much of the speculation about the possible sites for life elsewhere, or at least just organic chemistry, are based on hypothesized bodies of subsurface liquid water. We think that liquid water is essential for life and for chemical reactions, so wherever there's liquid water on other planetary bodies, these might be good places to search for life or study the chemistry that might lead to life. And finally, we've learned that Titan is a unique case of unusual organic compounds that might tell us something about prebiotic chemistry, the chemistry necessary to construct the building blocks of life. And therefore Titan is a laboratory that might tell us something very fundamental about the origin and evolution of life in the universe.